one of the oldest and the most familiar topic to mankind. Although this is something that many of us know a lot about, there are still yet few unanswered questions about solar physics, and answering them can unlock several mysteries and questions in the universe in different sources. So what are my contributions? What are our contributions in this study, and what have I been doing in the past 4 years in the PhD under the supervision of my supervisor? Let's find out. So on today's menu, we have some introduction and what is the motivation for taking up this particular topic, data and method, results, and my most favorite part of this topic for today is understanding the bigger picture of the results. Why is studying this important? So, introduction. Solar transients are different signatures on the sun. So the sun is one of the most dynamic sources in our solar system, and it's one of the closest sources to the Earth. And its dynamicity is mainly governed by the varying magnetic fields, due to which we see features like sunspots, prominences, flares, coronal mass ejections. Of these, the two main and the most powerful signatures on the sun are the solar flares and coronal mass ejections. Now, the most basic differences between these two are when flares occurs, there is ejection of photons, and CMEs are ejection of clouds of plasma. Flares take around 8 minutes to reach the Earth, whereas these CMEs take hours to days to reach the Earth. And flares produce something called as blast waves, which are shock waves. And in the same analogy, the shock waves produced by CMEs are called as interplanetary shock waves because they propagate in the space and they produce shocks. Now, what connects these two are two things. One is their production, which is caused by magnetic reconnection. When two magnetic field lines come close to each other, they interact and they explode, and the explosion is seen as the flares and the CMEs. Now, when such explosions occur, the particles that are surrounding the medium are accelerated by these explosions. Now, these accelerated particles from the sun are called as the solar energetic particles, which are basically electrons and protons that are relativistic. And this figure over here is a very nice figure produced by Gopalswamy et al. In 2019, which basically sums up the idea of the topic. So we have the sun over here, and there is flare eruption, and the photons and the particles are accelerated from this point. And you also have the coronal mass ejection, which is a cloud that is propagating, which also produces a shock, and it also accelerates the particles from that point onwards. Now, the key difference between these two accelerated particles are their flux profiles. So, a flare accelerated flux profile will produce a narrow peak like this, and the decrease of its intensity is quite fast. Hence, these are termed as impulsive SEP events caused by flares, whereas the particles accelerated by the CMEs gradually decrease their flux and they have a wider peaks. Hence, they get the name gradual SEPs. Now, coming to how they are occurring, the physical mechanism of their occurrence. So what we see over here is the magnetic reconnection that occurs, and there is particle acceleration from this point, and you also have the CME front over here that accelerates the particles. Now, the particle acceleration is mainly by the first order Fermi mechanism or diffusive shock acceleration, where the particles move back and forth from the upstream and downstream of the shocks, gaining energy and accelerating consequently. So the locations of location of the acceleration is at this point and at these points of the CME shock front. Now, how do we see these shocks? What are the indicators of the shocks and the flare accelerated SEPs? Now, the good indicator is solar radio burst. So solar radio bursts are categorized into 5 types: type 1, type 2, type 3, type 4, and type 5. Among these, the type 2 radio bursts are associated with CME accelerated SEPs and type 3s with flares. Now, how do we visualize them? When you look at a dynamic spectra like this, these structures, the vertical structures, which decrease its intensity quite rapidly, are known as the type 3s, which are caused by flares, whereas these gradual decrease of intensity in the radio, these profiles that we see are called as type 2 radio bursts. So radio bursts are basically energetic electrons that are unstable, which are converted into radio emission, and this is what we see in the dynamic spectrum. So using these profiles, we can determine what kind of particles are accelerated and what it is associated with. Now the next introduction is concerning the way the sun and the earth are connected to each other. So the idea is that particles need a roadway to be transported. So for energetic particles like protons and electrons, the roadways, the pathways are the magnetic field lines. Now the magnetic field of the sun stretches all over the solar system. And the way they are stretched are these spirals that are coming out of the sun, because the sun rotates in the anti-clockwise. So the magnetic field lines are carrying along with its rotation. And this is how the structures are seen. These are called as Parker spirals, as shown over here. So when an energetic particle is accelerated, they travel along the Parker spirals. And if the spiral is connected to the earth, the particles reach the earth. So the basics, that the introduction that I have given so far form the base of our study that we have considered. So what motivated us to take up this particular topic of research? So in the first 2 years of my PhD, I was concerned with studying the velocity and acceleration profiles of CMEs. And I had to constantly look at a particular catalog called as the Soho-Lasco CME catalog. And I had to see the variation of the CME with time and distance, which is shown in this middle panel. So as I was looking at this panel, I cannot stop looking at the other 2 panels above and below this, which shows the flux variation of the solar energetic particles and flux variation of the solar flares. So once our first paper was done, we wanted to see how well these 3 phenomena are correlated and associated with each other. Hence, with this curiosity, we took up this project and we went further. So this basically sums up what I was talking about, a statistical study. We wanted to conduct a statistical study looking at the correlation of 3 phenomena: flares, CME, and SEPs, which includes radio bursts. And we wanted to compare results from 2 different spacecrafts, SOHO and STEREO, and further on looking at its trend. And finally, we wanted to see its bigger picture, the contribution of the results in space weather forecasting. So these were the aims of our project. So when I conducted the literature survey for this topic, the topic isn't something new. Several publications were already made on such correlation studies of CME kinematic properties and the flares and the SEPs. And their individual correlation coefficients are shown in these figures. These were few of the results that I could fetch out and put it on the figure. So there are a lot of research that has been conducted. So what is new in our research? So the main thing that we noticed was all the previous research that were seen in the literature survey mainly used the Soho-Lasco data. So the problem with Soho-Lasco is that the spacecraft is placed at Lagrangian point 1, so that is in between the Earth and the Sun. So when you have to study a CME that is directed towards the Earth, the CME causes projection effect. So the accurate kinematics of the CME cannot be determined. So hence, this is one disadvantage of SOHO. And to counter that, disadvantage, we had to look at another spacecraft that does not give any projection effect. So coming to the rescue for that is our stereo SECI spacecraft. So the stereo is two twin spacecraft that is revolving around the sun. It's not at one position. So you have different point of views to look at ejections coming out from the sun. So that was first advantage. The second advantage is that the field of view of Soho-Lasco is just 32 solar radius. Now, the space between the sun and the earth is 214 solar radius. So 32 solar radius is a very limited field of view. Hence, coming again to our rescue, stereo offers the complete 214 solar radius field of view that we can use to study the variation of CME throughout its propagation in the interplanetary space. So that was our first key answer. The second thing that we noticed in literature survey is that most of the papers used average CME velocity for correlation studies. The problem with average speed is that this is an average of the complete propagation of a CME. We don't know what is happening in between its propagation. Hence, average will offer an approximate results for the study. So we did not want that. We wanted something that can give us much more accurate rather than taking the average speed. So what did we do for that? I will explain in the further few slides. So this was our new approach in our study. So data and method, let me quickly go through that. So as I said earlier, stereo spacecraft are twin spacecraft A and B that is rotating anti-clockwise and clockwise, offering a 360-degree view of the sun and its phenomenons. Now, how does it eliminate projection effect? Now, when you take this point of view on the side, if a CME is erupting over here and is moving towards the Earth, the spacecraft can clearly see its movement from the onset until it reaches the Earth. So through this way, it can exclude as much projection effect as possible. Hence, our data, the event selection, were based on this point of view, which is called as quadrature configuration of stereo, that is from 2009 to 13. So based on the quality of the images of stereo A and B, we chose the best quality of the CME and we proceeded with the event selection. Now, the 2009 and 13 that we have selected also marks the ascending phase of the solar cycle 24 over here. So this again gives us a different point of view of how CME energies are evolving from solar minimum until the solar maximum, half of the solar maximum that is moving on with. So this marks the ascending phase of the cycle 24. So when you want to visualize how a CME is seen in a coronagraph, this is a coronagraph that is artificial occulter of the sun. And the structures that you see is the coronal mass ejection. And at 4 UT, you see the CME erupting. And after 4 hours, you see the field of view is drenched with these particles over here. So these are nothing but the solar energetic particles that we see. This is how you visualize them. Now, to study the CME, we use comparative study of SOHO and stereo, just to make sure if it is better or not again. For CME flux profile, we use the GOES13, and for the flare flux profile, we use the GOES15. So from the period of 2009 to 13, we concentrated only on non-interacting CMEs, because interaction of CMEs will alter the velocity profile significantly. So we wanted to see how just individual CMEs are contributing to the study. And when you talk about the solar energetic particle range, we looked at 10 MeV energy range, 50 and 100 MeV, and we want to see what is the variation with energy range also with the associated CME. So based on this primary criteria, we obtained 38 good events for our statistical analysis. And when you place them on the sun, based on their longitude of the source location, this is the distribution of the events that we see. Now, what is important and interesting in this figure is that maximum of the events are placed on the western hemisphere and few in the eastern. So the answer to this distribution is, again, the Parker spirals or the magnetic field lines, the way they are connected from the sun and the earth. So since the lines are well connected from the west to the earth, we see our spacecraft detects majority of the events from the west and few from the east. So why do we still detect events from the east if the lines are not well connected? The answer to that I will answer in few slides. So let's come to the results. So let me just first quickly summarize what we see in this plot, which has a lot of lines. So firstly, this black line that we see is the coronal mass ejection, the CME velocity varying with time and distance. The CME velocity measurements are done manually by me. This is where my part comes in. I manually measure the CME propagation throughout until the time I see them in the field of view of the coronagraph. Now the red line, the blue line, and the green lines represent the solar energetic particles in 10 MeV, 50 MeV, and 100 MeV respectively. The CN lines that we see over here is the start and end time of the type 2 radio burst that is associated with the shocks. And finally, this dashed line that we see is the sum of the alpha wave speed and the solar wind speed, which forms the background speed that the CME has to travel with in the ambient medium. The orange line that we see is a velocity parameter, but we have loosely termed it as Mach number, which is very important parameter that I will discuss in detail in the next few slides. So the basic difference between this plot and this plot is that this is an event that erupted in the Western Hemisphere, West 66, and this is an event that erupted in the Eastern Hemisphere, far east at E89. Now, what I want to highlight in these two plots is that let's notice the delay between the peaks over here. You see the CME peak velocity is attained over here, and in just 1 or 2 hours, you see the peak of the SEP flux attaining. So for west events, the peaks are attained without much of a delay. But when you compare that with eastern events, the peaks are quite significantly delayed. So this is one major result that we would like to highlight of the delay of the peaks attained with the associated CMA and the SEP based on the longitude of their location. Now, using the peak velocity and the peak intensity, let's do some correlation studies. Now, as I said earlier, we would like to first compare the SOHO and the stereo data and see which one is the best and which is not so good. So comparison of these shows that the stereo correlation coefficients are much higher than the SOHO correlation coefficients. As I described the drawbacks of the SOHO, this is why we see the lesser correlations. And now, comparing only the stereo, this panel represents the average speed and this the maximum speed. So looking at the average speed correlation with the peak fluxes, we see that the correlation is much less compared to the maximum speed. So the answer to the summary of this figure is that it is good to use instantaneous velocity parameter compared to average parameter for correlation studies, as it is much more accurate and much more reliable. So this is what we see from these results, and these results were published in the summer of this year, and we move on from this particular results. So taking the primary results from the previous figure, we further constricted our study only with stereo data. With the stereo data, with the 38 CMEs that we took, we further made much more accurate manual measurements, and we again checked for the variation of average maximum speed. But this time we looked at the correlation with different longitudes, disk events, west events, east events, how the variation is varying with longitude, and we see interesting correlations that we have obtained over here. Now, I would like to just highlight the main points of this figure. So for all the events, irrespective to their longitude, we see the average speed again gives 0.69 correlation, which is okay. But when you look at the instantaneous maximum peak speed correlation, there is 0.70 correlation. So the problem with maximum speed is that, as you have seen earlier, for west events it is all right because the delay is not much, but when you move to events arising at the east, the delay is quite significant. So maximum speed will not answer the correlation study or will not give the precise answer to events arising in the eastern hemisphere. So we had to look for some other parameter that is suitable for all the events located on the sun. So to answer that question, we come to this parameter called as CME velocity at SEP peak flux. So when the peak of the SEP is attained, the consequent speed we take, and we see the correlation with the intensity, and we see that there is a very good significant improvement from the maximum speed. So we have 0.77 correlation for all events. So this offers to be a better parameter in studying events located at all longitudes. But we wanted to study and we wanted to investigate if there is a better parameter that can be used apart from just the velocity parameter, velocity that we have considered. So we looked at something called as velocity parameter, we have loosely termed it as Mach number, but there are problems with this terminology. So what this parameter tells us is that it is a ratio of CME velocity over the sum of alpha speed and the solar wind speed. The profiles of the alpha and the solar wind speeds were obtained by the models produced by these authors, and we call this Mach number, loosely termed. So let's see how this can help with the results, whether it is improving the results or not. So just to end the monotony of the presentation, since we are living at an unfortunate situation of pandemic, there was an interesting experience that I had in the beginning where few of my friends who knew I'm working on coronal mass ejections asked me, is the coronavirus caused by the coronal mass ejections? So I had to answer to them that no, it's not the sun, it's the terrestrial misdoings that is causing the virus. So just wanted to share a small experience that I had during this pandemic time. So moving on. So does the Mach number that we have termed offering a better correlation? Yes, it does. So there is from 0.77 to 0.83 improvement of correlation that we see. But again, as I explained, maximum Mach number is not suitable for events arising in the Eastern Hemisphere. So we moved on to looking at Mach number at SEP peak flux, which shows significant improvement in the correlation of 0.85, 0.77, and 0.71 for the individual SEPs. For Eastern events, there is 0.71 improvement of 10 MeV particles, but there is a decrease in the high energy profiles. Why does this decrease occur? Let me explain in the next few slides. So this was our key result of our manuscript, which we have submitted recently. Hopefully it might be accepted soon. So let's wait and watch. So in the past few slides, I looked at these one particular peaks of the CME and SEP. Now let's concentrate only on one particular event and the whole profile of the CME and the SEP. So for a Western event, when you look at the velocity, the variation of velocity over the SEP flux, we see that the correlation increases in such pattern. But when you compare this with Mach number variation with the SEPs, we see the correlation is improving slightly. Now, when you look at an Eastern event that is arising, we see a negative or an anti-correlation in the individual flux profiles of these two phenomena. So again, this concentrates on the magnetic connectivity of the sun and the earth, how the fluxes are delayed with the associated CME. So when the delay is much significant, you obtain an anti-correlation, and when the delay is not much, you have a positive correlation. And we check this for all the events of West and East, and we obtained positive and anti-correlation for individual events based on their longitude. So this was another key result obtained in our research. Oops. So finally, let's just look at the solar energetic particle intensity. From which point do we have higher intensity events and which one has less? So from 0 longitude up till 100 longitude, we can call it as the Western Hemisphere. We see more of the higher intensities SEPs arising from this, and lower intensity SEPs arising from this. So again, this is how the Parker spirals are connected from the sun to the earth. So the exact intensities of the SEPs are measured from the west, whereas you don't measure the SEPs accurately from the east. but still we do measure the SEPs from the east. Why? The answer to that is, as the CME evolves from the onset, the shock also expands. And when the shock expands, the shocks can connect to the Parker spirals that connects to the Earth. And when the shock fronts connect the Parker spirals, the particles start traveling along those magnetic field lines as well. And that's why we see few low intensity particles reaching the Earth, based on how well the shock is connecting and how wide the CMEs are. So this is a very interesting study that we do based on the expansion of the CME, how they are connected to different magnetic field lines. Now, if somebody asks me, Anita, how much time does the solar energetic particles take to reach peak flux once the CME erupts? So because it's the CME that first erupts and then the SEPs are accelerated. So to answer that question, on average, it takes 650 minutes for 10 MeV particles to reach maximum, 520 minutes for 50 MeV, and 500 minutes for 100 MeV. So what we notice over here is that as the energy increases, the time that it takes to reach the peak decreases. Why does this happen? So again, we come to a very interesting study over here, is that the higher energetic particles, that's the 50 and the 100 MeV particles, are known to be accelerated by the solar flares. And these particles that are accelerated by flares are called as seed particles for further acceleration in the CME shock fronts. So pre-acceleration of impulsive thermal ions that are accelerated by the flares are accelerated by the CME shocks. And due to this, we see that the maximum that the 50 and the 100 MeVs attain are much earlier to the 10 MeVs, because the flare contributes for the acceleration over here. The same when you look at the distance where the peaks are attained, we see that at 41 solar radius, the 10 MeVs attain the peak. Then you see 35 and 32. We see the similar pattern at distance also, which is contribution of flares for the acceleration of the particles. So this was another major observation that we made in our results. So this summarizes whatever I explained in this section of the presentation. Stereo offers the best data for conducting CME kinematic studies over SOHO data. When we compare instantaneous CME parameters, the best one to use is CME speed or Mach number at SEP peak flux as compared to maximum speed or the average speed. Electromagnetic waves such as X-rays and radio bursts travel directly from the sun to the earth, but energetic particles need pathways for traveling, and those pathways are interplanetary magnetic field lines or the Parker spirals. Delays in time and distance of the propagation of SEPs increase when we move from west to the east. CME-driven shocks can re-accelerate particles that are pre-accelerated by solar flares, and whose consequences we see in the results that I presented earlier. 10 MeV particles are predominantly accelerated by CME shocks, whereas the high energetic particles are accelerated by the flares. Now, coming to my most favorite part of the presentation, when a layman asks me, what is the importance of your study, Anita? What have you been doing in the past 4 years that can affect me? So when I have to explain a friend about the importance of my results, this is how I tell them. I introduce them to a topic called as space weather. Like the way Earth weather is affected by a lot of parameters, the space weather, which is the space between the sun and the earth, is largely affected by what is going on the sun. And depending on the phenomenon that erupts on the sun and the solar wind condition, the Earth's magnetosphere and the ionosphere changes radically because of them, which causes a lot of damage for airborne, spaceborne technology and as well as ground-based technology. So let me first talk about this particular tabloid that was published, which called it as toasted transformer. So the transformer that we see over here is the toasted one. So what was causing this? So when engineers and the scientists were trying to find out what suddenly destroyed the transformer on March 18, 1989, on careful analysis, they found that it was actually the sun. The space plasma did this, which caused a lot of dollars of damage and 6 weeks of outage of electricity. So let's just imagine a phenomenon happening like this during the current time of where the current time is highly dependent on electricity and technology. So there is damage on a very larger scale that can be caused by these particles. Hence, studying this field is of utmost importance for avoiding unimaginable damages that can cause due to that can be caused for technologies on space as well as the Earth. Now, when somebody asks me what is the most powerful solar storm that has been caused, I would answer to them saying that it is the 1859 Carrington event, where although we do not have technology as advanced as right now, the one indicator that we can know how intense the solar storm was is to look at the auroras that was caused by the solar storms. So basically, when we talk about auroras, all we think about is the polar regions, the countries in the polar regions that have good view of the auroras, like Norway, Canada, all these places. But on September 1 and 2 of 1859, the auroras were seen all the way down up to Cuba, Hawaii, Japan, and China. So that's how intense the northern lights were, and people actually woke up to the bright light of the northern lights thinking that it was the sunlight that was caused, but whereas it was actually the solar flare and the coronal mass ejection that erupted. So every object that we see in this slide can be affected by the coronal mass ejection. Astronaut safety, spacecrafts, airline passenger radiation, and all the way down to ground, the transformers, the technologies are all put to risk because of energetic particles coming from the sun. Hence, one must do precise calculation in prediction of when these particles arrive on Earth and how intense they are and what kind of damage they do. And this is what space weather scientists all over the Earth are dedicated to studying. So I would like to end my presentation saying that coronal mass ejections are beautiful as well as beastly at the same time. Thank you.
Thank you very much. Yes, I joined as well. So questions to ANITHA. So let me start maybe. In the plots that you were showing the intensity of the particles, yes, with the velocity of the ejection or the Mach numbers.
Yes.
So no correlations, like the distribution of them, then you talk about the correlation coefficients. So my question is, because we see that there is a correlation for the Mach numbers. Yeah, that's exactly what you were showing. Yes.
Oh, the previous one. Okay.
Yes, this one. Yes, so there is a correlation between the intensity of the high energy particles, right?
Yes.
And the Mach number. And so the correlation we see is positive up to Mach numbers around 1, and then there is no correlation. So is it not the opposite that one would expect if these fast particles are associated with the shock? Because the shock is only for Mach numbers more than 1, right?
Yes, yes.
So why do we see correlation when there is no shocks for the low Mach numbers, and then when the outflow is supersonic, there is no correlation, just the flux of the particle is steady?
Oh. Hmm. So there are few low intense events that we see in our in our um, in our sample that also are causing shocks much less than Mach number 1. So we see those events contributing to the correlation at less than 1. But what causes, why why don't we see the correlation higher than 1? I have no answer, sorry.
Okay, thank you. And just one question: there is so there is no errors here, or the errors are smaller than the sizes of the points?
The errors are smaller, the velocity
Okay.
errors are smaller. Yes.
So it's such a good measurement. Okay.
Yes, yes, it's good.
Any other question or comment?
If I may ask a
Yes.
question.
Please.
I was wondering, because SOHO is in the ecliptic plane as well, in Lagrangian point, and statistically, I would expect that measurements at SOHO place would happen to the Earth as well. So, couldn't you use those results from SOHO just statistically to compare what happens on the Earth, or the measurements on Earth are using different telescope and instruments for your work, so you cannot get everything from SOHO? I mean,
are you talking about the CME CME data or the?
Yes, on CME data, whatever you can measure, then statistically should happen to SOHO as well.
No. Sorry. Let me explain that. So this will give a good idea. So SOHO is located over here. So all the CMEs reaching SOHO are dominated by projection effects, whereas stereo can see it without projection effects, whatever is reaching the Earth. This point of view.
All right. Okay. Thank you. That's
I hope that answered the question.
Well, I thought about a different Lagrangian point, so this is the confusion.
This is at Lagrangian point 1, so I don't know about different points.
Okay, thank you.
Okay.
Any other question? I don't see, so let's thank the speaker again.